Hello, welcome back to the channel. Today we're looking at incline problems. However, this one is going to have a cable involved. So if we draw an incline like this, so it's a sort of triangle there. If we then, for example, want to look at we're going to obviously have the pivot on it, and then we're going to have a cable down here, and there you have the mass of M1G, and then on the incline you have a particle here, a mass here, the vertical downwards mass of M2G, and then a cable connects to that as well. So we have this system. Now in this system we have tension here, tension, we'll call it T2, and we have tension here, T1. So there's two tensions there from the cable, and of course you have the pivot. Now when it comes to this, what we actually want to look at is we want to look at the motion of the entire system. So to do that, we're going to start by writing out the forces. Now, from that diagram, I'll draw actually the way the forces are going. We can see quite clearly you're going to have, we know that from resolving things like this here, and from the angle, we'll call it theta, we can get the normal, and we can also get the sine value for the motion of it down, the force of it down on the incline angle. And when you get that, you're going to basically have this. You're basically going to have the sine angle of the motion down the incline minus the coefficient of friction times by cos of theta for the frictional force, and then you're going to have the minus tension force as well. So it's going to be like this. I'll show you. It's going to be like mass of 2g. That's not very clear. It's going to be like mass of 2g. So mass 2 times by gravity, sine of theta. We know that from earlier videos. That comes from the sine value down that incline. And then we're going to have the minus mu, the coefficient of friction, which is to do with the surface roughness of the particle and the surface roughness of the incline. And then we're going to times that by mass of 2 again, times by gravity, cosine of theta, because that's the normal force, which is the perpendicular force from the surface. It's always important to find the normal force in these problems. And that's going to equal to, sorry, that's not going to equal. But then you have to take into account the tension. So minus T2 is going to equal mass of 2 and times by acceleration. Now, the reason why acceleration, we are going to write out another equation first. I shall show you that first. As we can see from the diagram, we can see on the other diagram, if the whole system is moving this way, right? The whole system is moving this way. Therefore, that's the way we're resolving. We're resolving upwards, or not upwards, that way. Well, then, as this mass here is moving downwards, again, this mass here is going to be moving upwards. And you got the tension T1 pulling it up, and then you got the mass 1 behind it. Now, in this problem, we're going to assume that mass 2 is great. We're going to assume something very important. We're going to assume that mass 2 is greater than mass 1, so that we know that's going to be the direction of the system. If mass 1 was greater than mass 2, it would be the system would go the other way. Now, the next part is going to be defined as tension 1 minus mass 1 times by gravity is equal to mass 1 times by acceleration. Now, let's first talk about why does the system share the same gravity? Why does it share the same acceleration? That's an important thing to look into. The reason that it shares the same acceleration is because the whole system is a tight, inextensible rope, in the sense that the rope cannot change its length, and also the rope the rope is assumed massless. So we assume no mass for the rope. If we assume no mass for the rope, if we look at both the forces, so if we look at the rope parts like this, you got T1, and then you got tension 2. Because it's massless, we can first of all therefore look at the acceleration of the system of the rope as T2 minus T1 is equal to mass of the rope, so mass of R, times by acceleration of the system. Because mr is equal to 0, we know that mass of the rope is equal to 0. Therefore, with that, we're going to basically assume that tension 2 minus tension 1 is equal to 0, and therefore T2 equals T1. So we can just call it tension. We don't have to call it anything different. We can just literally call it T. Let's go to another part of the page. So yeah, we can call the whole system we can just call it tension. We don't have to give it a different name. So we're going to have now, if we look at this now, we're going to have now mass times by m2, m2g sine of theta minus m2g, the coefficient of friction, cos of theta. And then to similar to that, that's almost like a normal incline. However, we minus this tension value is equal to mass of the second mass, and then the acceleration of the system. Again, the whole system goes in the same acceleration because it's all connected in one inextensible string. So the whole system is moving at once. You know, we're assuming it's all going to be an inextensible string, no bouncing. It's just going to be one clear system. So we can define it like that. And then the next part is going to be the same thing, similar. It's going to be the tension minus mass 1g equals mass 1 times by acceleration. So we have it in that format now. So in terms of what to do next, as you can see, we have these two equations. The next part to do is if we add the equations, we can cancel out the tensions. So let's add them, and you'll actually cancel out the tensions. So if we go mass 2 g sine, so we're adding two equations, m2 g sine of theta minus mu m2g cosine of theta, and then we're going to literally add that m1 part, which is minus mass 1g, and that's going to equal m2a plus m1a. Now we can very easily take a factor of a out, and then we can divide by m1 plus m2. So you get it into the final acceleration form of acceleration of the system is equal to m2g sine of theta minus mu m2g cosine of theta minus m1g, and then divide the entire system at that over mass 1 plus m2. So we have a formula there for the acceleration. It's not that clear, but you've got acceleration is equal to mass 2g sine of theta minus mu m2g cos of theta minus mass 1g over m1 plus m2. That's how you get the acceleration of this entire system, which is important. Now, if we want to go further into the other parts, let's say we want to find things like the velocity, you'd have to use calculus. Now that's overcomplicate that. We're going to to keep the thing system. That's quite a complicated acceleration, so we're going to make it a little bit simpler. What we're going to do is we're going to make accelerations equal to, we're just going to call it, what we're going to call it is, for now we'll just call the entire system, we'll call the acceleration, I'm trying to think of something that won't be confusing. We'll call the whole system just accelerations equal to a of theta. It's a function of theta. That's what we'll call the system. Acceleration is a function of theta. Now we know acceleration is equal to dv by dt, like that. That's the acceleration value. And remember, acceleration, that a theta is equal to this value here. These values, m2g sine theta minus etc. It's just a way to make it clearer. It's a way so we can work with it. Otherwise, we're going to be working with a lot of algebra the entire time. Now, so for the next part, what we do is we do dv by dt is equal to that full acceleration function, and then with that, what we're going to do is we're going to well, we're going to get into this form here, where it's between velocity, the initial velocity, and the final velocity. dv is equal to the integral between 0 and time dt, like that. That's the form we're going to get into. The reason why is because it's actually between, time equal. It would actually technically be between time equals 0 and time, like this, between that, or from time equals 0, or from time equals 0 all the way to time, general time. That could be 2 seconds, that could be 5 seconds. Depending on where you are in the actual motion. However, we know that we can just easily define the whole system as time starts at time equals 0, as simplified. And we know the initial velocity is v0. We don't know it. The system could start with an initial velocity. If the system starts from rest, then we know v0 would equal 0. However, we can't assume it will definitely start from rest. We don't know that for a fact unless we do an actual example. But anyway, for this part, you're going to integrate that. So that's going to be velocity like that. We know that the integral of just 1, because that in there is actually the same as 1, is equal to v for dv, and that's going to be again between v0 and v is equal to, and again that's also 1, so it's going to be time. The integral of 1 is going to be of dt is going to equal time. So we're going to have t. So that's going to be like this, t between 0 and t. Now, for the next part, what we want to do now is we're going to get it. So once you do that, you get it into v minus v0 is equal to t. Sorry, that's wrong. It should have been, I apologize, it should have been a theta in there. That's a mistake. It should have been a theta. So that should have been, 1 second. Let me change that. Yeah, that should have been a theta t, like that. That's the form as you get it in between 0 and t. Not great writing, I apologize. Anyway, so once you have it in that form, we're going to get it into, and remember that a theta represents that acceleration. A theta represents that acceleration value we got before. It's a big thing. We don't want to write it out every single time. And what you're going to see here is is basically suvat being defined, because remember, suvat it comes from calculus. If you haven't got to this point yet in mechanics, suvat is fundamentally just from the idea that acceleration is equal to the derivative of velocity with respect to time, and then velocity is equal to the derivative of displacement with respect to time. Once you have that relation, that relationship is very important in any kind of dynamics problem. The next point, as you'll see, it looks the same as the suvat formulas we know, because we're basically deriving suvat. For the next point now, what we want to do is we want to get the displacement. And displacement we know is, we can write it like this, dr by dt is equal to velocity. We know that. So therefore, we can write it as dr by dt is equal to v0 add acceleration theta time. And therefore, we're going to have the integral between the initial displacement, which we don't know for sure. It could be 0, but we don't know for sure if it is 0, and r, the general r value that we're at currently. And then what we're going to do is dr. And remember, that's just going to be 1 in there. You have to remember that integral. That's just going to be 1. So it's that integral and that'll just be r, and then that's going to equal the integral between 0, time equals 0. So the integral between time equals 0 and t of v0 dt plus the integral between 0 and t of a theta t dt. So that's you see now we're getting the actual integrals in it now to get the derivative, to get the displacement. We know that's going to again equal r, like that, between r0 and r is equal to v0, that, and 0 and time. Sorry, that's wrong. It should be v0t. Let me just, like that. Add, and this one's more interesting, a theta And we know that the integral of that is going to be t squared over 2. I'll be happy to do a video on integration if this is something you'd like me to cover, and 0 and t. So we have it in this form now. So we are basically deriving suvat here. You have it in that format now. And then basically you're going to get into the format of r minus r0 is equal to v0t plus a theta t squared over 2. That's the format there. And you can see this is basically suvat we're deriving. So this is the displacement along the actual incline. And in terms of, if you want to know, for example, how long it takes for the system to crash into the pulley, if we know that the distance to the pulley for M1, let's say for mass 1, the distance to the pulley is going to be length, right? Then all we have to do basically is we put that into the formula, length minus R0 is equal to V0t plus a theta t squared over 2. Now I'm going to make this a bit easier. I'm going to times out everything by 2. So we're going to get into 2 length minus R0, like that, is equal to 2v0t plus a theta t squared. So you got in this format now, and then this is basically a quadratic equation. So we want to rearrange it to get it into this form here. A theta t squared add 2v0 t minus 2r minus l. Oh, sorry, I apologize. It should be L minus R0, like that, is equal to 0. Now that's a quadratic equation. But yeah, so the idea is that if it has to move L distance until it reaches that pulley, if we're assuming that, in reality we could measure how far away it is from mass 1, which is the hanging mass, to the actual pulley, we could then know, therefore, that we could plug the length in, and we could work out how long it's going to take until that pulley crashes in. Until that particle crashes into the pulley.